Welcome to today's webinar on marketing mix models with Bayesian networks. Thank you for joining us for today's event. My name is Stefan Conradi, and I will be co-hosting today's seminar along with my colleague, Dr. Lionel Jouve, who is joining us from his office in France. Hello, Lionel. We have quite a bit to cover in the next hour, so I will try to keep my introductory remarks fairly short. However, I should mention a few administrative things. And that includes that this webinar will be recorded and posted to our YouTube channel. That channel is youtube.com/Conradi Science. And also, as far as questions are concerned, we would ask you to submit those questions via the chat panel. We may not have time to respond to them online, but we'll definitely get back to you after the webinar. Also, I'd like to encourage you to download a trial version of Bayesian Lab, which will allow you to apply the approach Lionel is presenting today on your own problem domains. And you can get to this download via our websites, conradiscience.com or bayesian.com. Here's a quick agenda of today. I will briefly provide some background as an introduction, but then really the principal focus of today is the software demonstration from Lionel. So here is a famous quote. I know I waste half of my advertising dollars. I just wish I knew which half. This kind of reflects a century-old uncertainty about the effectiveness of marketing instruments. This quote has actually been attributed to John Wanamaker, who some consider to be the father of modern advertising, as well as Henry Ford and J.C. Penney. But I think you'll all agree with me that back then, the advertising and media landscape was certainly a lot simpler. And without doubt, with all the new media channels that are emerging almost every day, there are many more marketing instruments that someone has to consider. So the questions of how to allocate your marketing resources is more important and more difficult than ever. Given that this has been an issue for a century or so, and given that the total media spend in 2012 is estimated to be about $152 billion, one would really expect that this domain is extensively covered in a wide range of textbooks. But surprisingly, this is not so. Although I don't claim I've done an exhaustive search on this, it seems there are really not a whole lot of titles available. I just looked at Amazon the other day, and I felt there were only really 2 or 3 books that were really relevant to this particular topic. In contrast to the very small selection of books that are aimed at the practitioner, there's a huge body of specialist marketing science literature in academia. As interesting as much of this research is, most of it is barely accessible to a practitioner, and virtually none of it is easy to implement. However, there's clearly no shortage of vendors who promote their solutions in this particular field. We've just Googled the keywords and collected some of their claims from their websites and white papers. And looking at their headlines, one really gets the impression that attaining the marketing nirvana is indeed possible, or it seems that you can master the marketing mix. These are really, really bold promises. Unfortunately, as you look at some of these white papers, and I'm kind of exaggerating to make my point now, none of them offer a whole lot of detail on the processes and the techniques that are employed to get to the proposed nirvana. So one wonders how marketing science consultants arrive at their recommendations. I suspect that in many cases, one would be rather disappointed to learn how much human opinion hides behind great visuals and elaborate graphics that we find in some of the glossy reports. Also, some of the software solutions that we see being offered today are very often like black boxes. They may be very sophisticated inside, and for all we know, they could indeed be very powerful. But the challenge is that end users, the ones who use the results that come out of these black boxes, may not be able to validate the mechanism leading to those results. So Bayesian networks are just the opposite. They are meant to be entirely transparent, and they are meant to be read and interpreted by anyone. One does not need to be a statistician to understand them. Quite simply, in a Bayesian network, nodes represent variables of interest. For instance, sales, budget, GRPs, website hits, customer churn, response rate, credit score, what have you. The arcs or arrows that connect the nodes tell us how these variables are related to each other. Between the nodes and the arcs, we have really a complete representation of our domain. In today's example, this domain includes marketing instruments plus a variable or plus a number of variables for the outcomes we want to optimize, such as sales and profit. If you will, Bayesian networks are really the CFO's best friend, as they allow auditing the model that the market researcher develops. One can literally trace each arc between the nodes and thus get an understanding of how the domain appears to work. Now, our team certainly has not invented Bayesian networks. It was actually Professor Judea Pearl at UCLA who first proposed Bayesian networks as a form of knowledge representation in the mid-1980s. And since then, a very large body of work has emerged covering all aspects of Bayesian networks. And there are obviously many more things to say about Bayesian networks and their specific properties, but given the limited time today, I would like to refer you to some of the white papers and the book recommendations that we have on our website. Now you will ask, how do we obtain a Bayesian network of our domain? And a traditional way has been building a network by hand based on expert knowledge. However, in many cases, this is exactly what we're lacking. We don't have the expert knowledge yet. We don't really know yet how all these marketing instruments interact. And this is where knowledge discovery from data becomes very important. Instead of hypothesizing about how something works, we machine learn those dynamics from data. And once we've learned that the mechanism, we can then analyze the system and perform all kinds of simulations and even search for perhaps an optimal outcome. Well, how do we do all this? So this is where our software comes in, Bayesian Lab 5. We use literally Bayesian Lab for all of the above, for everything from machine learning all the way through optimization. And Bayesian Lab is really the only software that integrates all these aspects of managing Bayesian networks. All this is contained in a single platform. Shortly, you will see Lionel showing Bayesian Lab on a Mac, but as Bayesian Lab is a Java-based program, it will run on all platforms. Let me now provide you with a conceptual overview of what Lionel will soon present in the software demo. Our starting point is observational data, such as observations of marketing-related data over time, as I mentioned earlier, impressions, hits, GRPs, media spend, sales, etc. And from this data, Bayesian Lab will learn an abstract representation in the form of a Bayesian network. This is meant to capture all the dynamics that were contained in the original domain. Once we have that representation, we can experiment with this domain and create hypothetical scenarios, such as, well, what if I were to reduce my print advertising, and what if I were to increase my online advertising? Of course, with many variables, there are endless possibilities of how to allocate all these marketing resources. And that's once again where Bayesian Lab comes in and does the work for us, because Bayesian Lab can search among all the combinations for an optimum mix. So this is really the objective of today. We want to show you a workflow in great detail, literally step by step, almost like the way you would see it in an assembly instruction from IKEA. The idea is that you go from the data you have, the status quo of your marketing mix, and then step by step go through the methods proposed all the way to obtaining an optimum marketing mix recommendation. So now, without further ado, I'd like to make Lionel the presenter. Let me switch here the GoToMeeting presentation. And then the floor will be all yours.
Okay.
Lionel?
Yeah.
Has
Hello?
this... okay, hold on. Okay, here we go.
Good.
I think once you share your screen, and there we have it, we are in business.
So you can see my screen?
Yes.
No problem. You can hear me?
Perfectly.
Good. So hello, everybody. Yes, as Stefan said, I will just try to show you in 40 minutes or so how we can use the very last release of Bayesian Lab. And when I say very last release, this is the release of today. How we can use Bayesian Lab for trying to optimize marketing mix channels or mix the channels for optimizing sales. So the idea here is first, so as usual, I'm using my mind map examples just to describe how I will present these things. So the first thing I've made is define a Bayesian network by hand first to generate, a data set. The problem is we don't have any data sets we can share with you, and then I had to first design a Bayesian network by expertise, and then use this network in order to generate a data set that represents the joint described by this network. And as you can see here, I have a Bayesian network where my target variable here is sales, and it depends on TV advertisement. It depends also on the season, on online advertisement, on radio advertisement, and print advertisement. And print is divided into 3 sub-prints, if you want: national, regional, and local print. And we also have here the profit, which is directly dependent on the amount of sales and also on the conversion rate between euro and dollars. And just in order to use this data set also to show you how we can handle very easily missing values, I've also used this network in order to generate missing value completely at random for TV, meaning that I will not use the real TV data, but use the TV with missing value, and the generation scheme here is just purely random, meaning that I'm selecting 15% of the data and removing it here. So this is completely at random. I also have the missing at random for online, meaning that now the generative process for missing value depends on the level of impression. So, and I've just choose randomly here. When the impression is lower than 0.5, then I'm increasing the probability of having missing value for online. And the very last one, the third type of missing value, is not missing at random. So this is a worst case scenario here, where the missing value depends on the local print value itself. And here I just choose to increase the probability of having missing values when the value of local print is higher than 0.7. So just, yes, a few words on that. Everything here has been normalized, so most of the variables are between 0 and 1. So I'll then use this network in order to generate 50,000 data points, and then have a big data set with missing value. Then I will use this data set, import this data, and I will have 2 types of variables. I will have continuous variables and one categorical variable for the season with 4 states. And then I will have to define what will be my algorithm I will choose in order to deal with my missing values. And I will show you a very special way to deal with missing value. As you will see with Bayesian Lab, we can use structural expectation maximization. But here, I just want to show you another workflow consisting in using static completion, but by doing, defining a workflow with first maximum weight spanning tree, then probability learning, and then EQ. I will just show you that in order to be very, very fast. And then I will use the Opten model in order to do target mean analysis, first with total effect, and then with direct effect, meaning that we will analyze the effect of each variable by holding fixed all the other distribution of the other variables. And after that, we will use that model in order to try to find the best marketing mix. And then we will first make one simulation when we don't have any additional budget, and another one where we will have additional budget, and we will see what is the output, the outcome. So let's go with this new release, which is indeed 5.07 now. So I will open my data source, which is this one. So as I said, I have next here, I have 50,000 lines, 50,000 data sets. So you just have to imagine perhaps it's over 2, 3, or 4 years. I don't know how many samples I can have per day or per shops. And then I have 13,000 missing values, 12 continuous variable and 1 discrete, which is the season. I click on next here. And now I have to define what will be the algorithm I will choose in order to deal with my missing values. So I will, as I said, use my static completion algorithm and then describe how it works when I will show you how we are going to learn the structure of the network. Click on next, and I now have to define what will be the discretization scheme for all my my continuous variable. And here the idea will be to use equal distances into 5 steps. So I'm just selecting all the continuous variables and go there, equal distances into 5 pins, and click on finish. So I'm loading the data. I will have 1 variable per column, and I have this network. You can see, zoom here. I have 1 variable for sales with small white points around the node, just in order to indicate that this is a continuous variable that have been discretized. And as you can see, all these variables have these white points, except season, who does not have any point, because this is a discrete variable. And we also have this question mark on these 3 nodes, just to indicate that we have missing values associated to this variable. And if I press I while hovering over my question mark here, I have the number of missing values. So here I have 7,445 missing values for TV, 4,000 for online, and 1,600 for local print. And so now the idea, just before going learning process, I will perhaps describe how it works with the static completion. So when you can choose what algorithm you are going to use in order to deal with missing value, you can choose that during the importation wizard, or you can also just go there, learning, and choose here among the 3 options, missing value processing. Then you will be able to change it while learning or while analyzing your model. So we will start with the static completion. And what does that mean, static? That means that at the very beginning, we have some information, for example, on TV. We know, given the value we have, so we have here 43,000 observation for TV without missing values, as we have 7,000 missing values. And given these 43,000 values, we can compute the probability distribution on this variable. And we will use that in order to fill to make the imputation. So we will have 2% of chance to impute something greater than 0.8. And we'll have 10% of chance to impute something between 0.8 and 0.6 and so on. We will do the same thing for online and the same thing for local print. Okay, so we will use this current knowledge. So given we don't have any connection with TV and other variables, so we just use this marginal distribution in order to make the imputation of the 7,000 missing values for TV and car. So this is the first step. And then we will use structural learning. And just before using my maximum weight spanning tree here, I will perhaps just say a few words about how it works. Because as Stefan says, this is not a black box, so we can just describe how the structure will be discovered. And then the idea is to we are using a score which is mainly based on information theory. And when I say information theory, I'm speaking about entropy. And let's suppose we will focus on sales for the moment. We have this marginal distribution for sales. Zoom in here. And given that distribution, I can compute the entropy. So if I make a right click on this node, I can compute the entropy here. And my marginal entropy is 2.03. And just to say that this entropy is the minimum value of the entropy is when we have one state with 100 and all the other states with 0%. If I do that, entropy will be 0. But it will be the maximum value will be obtained when I have something with a uniform distribution. So I have 25, 25, 2 other one, which not 25, 20 indeed. If I do that, even this kind of distribution, then I will have a high entropy. So this entropy will be the highest one when we have a uniform distribution. And now, given this entropy, this marginal entropy, we will try to find, is there a link with sales and, let's suppose, season. So I will just add a link between season and sales. My link, and then I will compute what we call the expected entropy. So for season, we have 4 states. So I will double click on 4 just to say what will be the new entropy of sales given 4. So I double click on 4 and I got a new probability distribution and then a new entropy. So I will compute this entropy and it's 1.94. So it's lower than the marginal one. Then I will do the same thing for spring. And then I will have 1.98. The same thing for summer. I will have another entropy, which is 1.87 here. And the last one, winter. And then we have again a new entropy, which is 1.87. And then we have here a uniform distribution on season. So we would just make, it's almost the mean of these 4 entropy we had, these 4 conditional entropy we had with season. And we will subtract the marginal entropy of sales minus the expected entropy given all these 4 states. And this is what we call the mutual information. And this is a kind of correlation matrix, if you want, that is not linear and so on. And the MDL score we are using in order to build the structure, to find what is the best structure of our network, is based on this mutual information part, but also on a structural complexity term, if you want. So the idea is we will add a link between 2 variables when we have high mutual information and where it's worthwhile to add this link in order to gain this knowledge. If it's just a very small mutual information, and if we are going to increase a lot the size of the conditional probability distributions that are inside each node, then we will not add the link. Okay, so we are always, so this score is twofold, one part for the mutual information and the other one for the structural complexity. So we will not do that manually. So we will just here remove the link between season and sales, and we'll use our structural learning algorithm. So as I said, the very first step is we have imputed all the missing values of these 3 variables given the marginal probability distribution of these 3 variables. And we will, so for the moment, internally, the structural learning algorithm will just consider that we don't have any missing values. So it will be really fast. So I go there and I will use the maximum spanning tree. Be almost instantaneous. Here is the result of this maximum weight spanning tree. So if I press P key, I have this new layout. And now this is my new state of knowledge, if you will. So I know that I have a link between local print and overall print. I also have a link between TV and season. And I have 3 links indeed with online. So online is connected to sales, hits, and impression. And then now, rather than just using the marginal probability distribution of online in order to make the imputation, I will use the value, the observation I have on impression, hits, and sales in order to make the imputation on online. And I will do the same thing for local print, just by using overall print. And for TV car, I will use season. I just use one example. Before, for online, I was just using this marginal probability distribution. And now, let's suppose I on a line where there is something here. This is the observation. So given these 3 input, I will make the imputation in this new distribution. So I will have something much more precise. So I'm removing the evidence, and given that new network, that new knowledge, I will again make one step of imputation. So I will go there, because if you want, static imputation is a kind of imputation on demand. So I will go on probabilities learning, and then by doing that, I will make a new imputation by using this by the network. If I do that, you can see now the missing value have been imputed, and I will be able to use EQ. Use EQ, and I have this new structure. So make some here. Have my V car. So now this is my new network obtained on data where all the missing values have been imputed by using the maximum weight spanning tree network. And then I will again make another step where I will use this network in order to make the imputation of all these missing values. Again, I will go there, learning, probability learning, and imputation. And now I have another data set with imputation by using this network. We go to learning, EQ, and again, learn the network. And here we have exactly the same structure. So I don't have to continue. I will just go there and go back with structured EM. So meaning that I will not use any more imputation, and will make the very last step, which consists in estimating the probabilities given that network, but without doing any imputation. So it's longer, and now it's okay. So we have our network, and all the missing values have been taken into account, and we have probabilities associated to these missing values. And now I will go into my validation mode. I will remove my monitors here, and we will start analyzing this network. Let's go to analysis, visual, and the first thing we can do is just to see what are the strongest links. And we can see by using the arc force analysis, we have the thickness of the links that is directly proportional to the strength of the relationship. And here we have 2 really strong relations. The first one is online hits, and hits and impression are indeed some kind of sensor of the online advertisement. And then we will be able to analyze just to see if it's really strong. So let's suppose hits are high. Then here was deterministic association here. Here you can see that this is indeed a very strong relation. And the second one is this one, sales profit. Again, just see what happened here. Even associate Euro USD conversion. If I say that the profit is high, then we are back propagating this evidence towards sales. And if I say that the euro it's 1.6, then the sales is just moving a little bit. So we have this relationship. So here the information is going in all these nodes. I will remove all the evidence, so we can just play with the network like that. And now the idea is we have a target variable, which is sales. So I'm just pressing T and double clicking while maintaining T press in order to define this node as a target. And I have here my sales monitor. And I will perhaps just the first thing to do is to use the analysis visual, and here's this one, influence analysis on target node, just to have this kind of analysis, just to see. So the first state here, the first tab, corresponds to the lowest value, 0.387, where we have a probability of 2.11. And we can see that the most important variable is profit margin. This is here you can see that what is the probability of having a low sale given the different states of profit margin. We can see that a low profit margin is increasing a lot. The probability will be 32 for a low sale. And then this is the same thing with our print and so on. We can see that with season, low sales correspond to summer. If I go in the other direction with high sales, then we will have high margin. And if we have a look to the season, this time the high sales correspond to winter. Okay, so when we are in winter, we are increasing the probability of having high sales. So this is one way to analyze this target variable, just to have, so you can just read the importance of each variable. This is the most important one, the one that brings the more information, the second one, the third one, and so on. And each one depends on the values. But here sales is indeed a continuous variable. We have defined bins in order to be able to deal with it in BasilLab. But at the end of the day, it's a continuous variable. And here we have associated to each bin, we have computed what is the mean of the points that have been associated in that bin. So for example, this is a bin corresponding to the high sales greater than 1.2. We can see that the average or the mean of the points that are in this bin are 1.376. And we have this mean value for each bin. And given these mean values, we are able to compute what will be the expected value by using each value associated to the bin plus here the marginal distribution. And then by using that, now we will really make an analysis in the continuous world, if you will. And we will just do that with visual and target mean analysis. And the first one, we will do the standard one. Do that. And I can display the sensitivity chart, and we have this graph. So here, just a few words on this graph. We have on the x-axis, it depends on the values of all the other variables, and on the y-axis, this is the mean of the target. And here I just display the delta versus the delta. So at 0, 0, this is all the average or the current mean of all the variables. So we are just using the marginal probability distribution of all the variables, and this is the origin of the graph. So now you just can see that if I'm increasing this green curve here, correspond to TV, so we can just analyze that by saying if I am increasing by 0.20 or 0.4, then I will increase by 0.20 the mean of the sales. And here we have a strong relationship with the profit. We have some nonlinear relationship here with the print and so on. Have this one to online. You can see we will have to probably to decrease the online advertisement in order to increase the sales. So we have a kind of overexposition here. So if we are displaying too much advertisement, then we are reducing the sales. And so this is just, yes, moving. So if I just make one interactive inference just to show you how it works, the idea is just to say here, I take online, increasing a little bit the amount here. I will say the mean is now 0.65. You can see decreasing rate of sales. And as you can see, I also have some impact on all the other variables. So the idea will be to say, well, now I don't want to allow the other variable to move. It's just I'm going to do something online, and then I will not change the radio and so on. So I will fix all the other variables. I will fix all my variables here, and just say I will play online. If I say now I want plus 65, then I'm computing the effect of online, but without moving any other drivers. And this is exactly what we are going to use when we are going to use the analysis here with the direct effect. So this is not the same thing as the first one. This is also based on the confused value, but each time we are moving the mean of all these variables, we are holding the distribution of all the other one fixed. So we are just computing the impact of all these variables, and we have the chart. So let's focus, or for example, if I go there, we will see that national print, regional print, and local print do not have anymore any impact. And the reason is just because we have this variable overall print. So if we are moving national print without moving this overall print, then there is absolutely no impact on the cells. And this should be the same thing for hits and impression, because we have online here, which is on the path of sales. So I go there with hits, and where there, as you can see, you can see that this is moving a bit. This, hits is flat, and it should be the same thing with impressions. Okay, so we can see that we have all these relationship. Now we can see that TV is not anymore linear. We can see that we can see almost here another exposition too, as it was the case for online advertisement. And here we have set everything was in the fixed variable. But what we can do now, it's a kind of causal analysis and saying, well, when we are fixing is just because we are thinking the variables are kind of confounders. And so here we will use expert knowledge just to say what is or is not a confounder. And so, for example, here, profit and euros are not confounders. They are not the cause of the sales. So we will just use these two variables, make a right click and define a class, which is a predefined one, non-confounder. And then we will not fix their probabilities, meaning that if I'm increasing the TV advertisement, then I will increase sales and I will also increase the profit. And in the previous analysis I've made, I was just increasing TV, but without moving, without any impact on profit. And I will do the same thing for these two because they are absolutely non-confounders. And do the same thing with this one, which is a kind of synthesis. So I just want classes here had non-confounders. So just to be sure, I will associate a color to all these confounders. Let's say it's green. So these green variables will not have their probability distribution fixed when I will move these yellow variables. So now I will do the same thing. What is this? Visual, direct effect. And here I have my relationship. So as we can see, the TV has clearly an overexposition problem too. This is the same thing with my online advertisement, and it's also the case for the radio. And here this is a season. So here it's quite artificial because season has been transformed as a continuous variable, even if it's not a continuous one. Here it's clearly, I guess this is winter, and here it's summer. So the idea now is we are going to use this network and to try to find what will be the optimal mix. Okay, and so we first have defined what were the non-confounders, so all these green variables, and we need now to also say that we will not be able to have any impact on season. So season, even if it's a confounder, so we know that we have this variable as a direct impact on sales, even if I'm fixing everything. So this is something, this is a cause of sales, but this is not a driver. I cannot control season. And then I will just define a cost, and I will say that it's not observable. I will not be able to change the value of this season node. And all the other variables, so the 6 remaining variables, are potential drivers. And now what I will do is just associate, as all my variables have been normalized, I have to associate a dictionary of cost in order to have realistic costs. So I go there, associate dictionary, node costs, and use my cost USD here. And if I have a look, in this dictionary, I've just defined that local print, the cost for 1 unit of local print is 1,000 bucks. For national print, it's 100,000. For online, it's 100,000. For radio, it's 10,000. Regional print, that's the same, 10,000. And for TV, it's 1 million per unit. So TV, increasing the TV advertisement will be really expensive. And the less expensive is local print. So given this information, now I will use my target dynamic profile, so the features that will allow you to try to optimize the mix, the marketing mix. So you go there, analysis, and then report, then target analysis, and then target dynamic profile. You use this feature, and we will first, as I said, the very first trial will consist in, we don't have any additional budget. We will try to optimize the mean, so we want to optimize the mean of sales. We want to maximize this mean, and we will use, here we are not going we are going to search among all the domain of the variables. So we are just checking domain here, and we will edit the variation just to say that we are able to search from 0 to 1, if you will, in my normalized domain here for all my variables. And I will define how many numbers of intermediate points I will estimate for each of my drivers. And so here I define 50 points, and I will use the direct effect, meaning that when I will change one mean, one value of one driver, all the other one will remain with the exact same probability distribution. I am defining what will be the size, the maximum size of observation of drivers that I will use. Here it's 6, and I will use my automatic stop criterion just to say that perhaps it's not worthwhile to continue changing anything. And here it's the maximum budget or delta of budget allowed. So as I said, my initial budget is 445,000, which is computed with respect to all this current mean on all these variables. So given all the past, the mean of my budget is 445,000. And the idea here, I'm just trying to see what will be another policy with the same budget. And then I'm just trying to do that. So we are carrying out this analysis. And here we have this report. So how can we read that? This is the first line. This is the a priori. So when we are not doing anything, so this is the average. The a priori when we are using all the marginal probability distribution on all these drivers, the budget is computed with the cost I've associated before. So my initial budget still is 445,000, and I have the mean of sales, which is 0.872. Which is here. And here, by using this optimization process, the idea is just to first to decrease the online marketing. Just the initial value was 0.55, and the idea is just to reduce it to 0.48. And if you remember well, we had indeed an overexposition problem with this variable, and we were already overexposing our customers. So the idea is to reduce the budget allowed to online marketing, and then we will save money here. So even if we said we don't have any additional budget, as we are doing some economy here, we are gaining or saving $6,077. And even by doing that, we are increasing the sales. And then, as we have more money now, we can increase regional print. And so from 0.379 to 0.502. And then once we have, so decrease online, increase regional, and now we will increase local print too. We still have some budget, and at the end of the day, we will increase national print. And then we just have 454 budget, but it's not enough to do any additional action. And then here, without having any additional budget, we are able to increase the sales value from 0.8772 to 0.921 without, spending more money. So this is the first one. And now let's try another one where we will say, okay, let's see what happens if we can spend $10,000 more. So again, we will use this. So we will be able to spend $55,000. And here it is. We have our new marketing mix where, so if I just want to keep this one too, and as you can see, we at the end of the day we have spent $9,500 more, and we have increased our regional print, then increase local print, then increase the TV advertisement, which is really expensive, then decrease online in order to save money, and increase national print. And we are, reaching the level of 924, the value of sales. And so as you can see, we can try a lot of different budget. And if you just want to see what happened, and just use the monitor there, we will just again define this season as observable, because we will just use the evidence. So I will make a right click on this scenario icon just to play the very last one. So I'm just clicking, making a right click here, and then I'm able to select this one, and then I can see what happened with the very last action. So this corresponds to this one, where I have increased regional, local, TV, decrease online, and increase national. And this is the exact same policy here, and we get this 924 on sales. So I think we just have 4 minutes, Stefan. I don't have any more time to speak about missing values, so
Well, thank you very much, Lionel. This was a very interesting demo. Allow me to switch back here to my screen real quick. Just bear with me as I... Okay, here we are. Yes, well, thanks again, Lionel. This was really, I always enjoy listening to your software demos. I feel like I can always learn quite a bit. So I hope our audience found this interesting and valuable as well. There are quite a number of ways how you can learn more about Bayesian networks and Bayesian Lab in particular, such as in our upcoming training seminars. And 3 of those we have scheduled for the rest of the year here in the US. First one coming up in Boston, June 26th through the 28th, then one in Toronto in mid-July, and yet another one in Silicon Valley around the data mining camp in mid-October. Another great way to learn more about Bayesian networks is to join our online community on LinkedIn. And this is actually where we'll also post questions and answers to all the questions we received. So you may want to check that out. Also, we're getting very close to 1,000 members. So if all of those of you who have not joined yet join our group today, I think we'll reach the 1,000 member threshold. And of course, we wouldn't be a modern organization if we didn't have a Twitter feed. You can follow us at Bayesian Network for daily nuggets of knowledge about this topic. And as I mentioned earlier, the recording of today's webinar will be posted on our YouTube channel. That is youtube.com/ConradiScience. And there you'll find recordings of previous webinars as well, plus, of course, today's webinar. And, well, this concludes today's webinars. And I would like to thank you for your interest. And please allow me to remind you that you can download the Bayesian Lab trial from our website. And, of course, you can find many white papers and book recommendations there as well. And you can always email us or call us with any further questions that you may have. Thanks again for participating, and have a great day.